On a family trip to India, I saw the glaring water gap. There was a lack of access to clean water, and many people, including myself, fell ill from drinking microbial contaminated water. When I returned home, I found that this was a global issue. 2.1 billion people across the world lack access to clean water, and an estimated 1 out of 3 drinks from such severely contaminated water that they are at severe risk for waterborne disease. And the current solutions are simply not up to par. On the consumer end, we have test kits and test samples, both of which require the consumer to manually check for contamination themselves, have a high risk for false positives, and can be inaccurate because they depend on factors such as pH to determine if there is any contamination present. pH can vary greatly depending on where your water source is from, thus meaning that this is not the most reliable system. They also require multiple kits to check for all the kinds of contamination, thus making them expensive and inaccessible. On the municipal end, as per the Greater Cincinnati Water Works, while there are checks for microbial contamination in the water plant, such as granular activated carbon, which helps to remove any organic matter that may still be present, there are no reliable and consistent methods to do so once water leaves the water plant and enters the distribution system. So my problem was the lack of access to an early and affordable water contamination detection system, and my initial solution was to use a neural network program that can rapidly and accurately detect microbial contamination in water through the analyzation of microscopic images of water. I then designed multiple design success criteria for the success of my device. Firstly, I wanted to ensure that my neural network had an accuracy greater than 90%, be able to identify both the type and the presence of any microbial contamination, and have an all-in-one cohesive device that can directly be implemented into water plants and water distribution systems to check for any microbial contamination before it spreads too far. I began this process by collecting and validating my images. I did not have access to a traditional laboratory environment, and there were no public domain microbial images that I could do. So I created my own data sets using non-toxic microbes, such as Lactobacillus, Streptococcus thermophilus, and Saccharomyces cerevisiae. I then created various combinations and solutions of these microbes and took 3,000 images. I then divided them in a 2-to-1 ratio for training and testing. I then divided these images into their various classes, such as clean, Lactobacillus, Streptococcus thermophilus, and Saccharomyces cerevisiae, alongside the multiple combination solutions that I had, because I wanted to ensure that even if there were multiple types of microbes present, my device could still be able to identify all of the microbes that are present. I then performed some image resizing and feature extraction on these images. For the image resizing, I resized them all to a 227 by 227 vector with 3 RGB channels. I also noticed there was a lot of background noise in some of these images, so I performed a median filter and a contrast filter to remove some of this noise. One example of such noise would be Brownian motion, where due to the natural tendency of liquids, the water would move, thus causing the microbes to move and leading to blurry images. I wanted to ensure the highest level of clarity possible, and here you can see a before and after of the images once the filter was applied. I then extracted the features that I wanted my neural network to focus on instead of background changes in things such as concentration or color. And the first feature that I chose was shape. Microbes vary greatly in shape, and the two that I picked were cocci and bacillus. Cocci are very round-shaped microbes such as Streptococcus thermophilus, and bacillus are more rod-shaped and elliptical, such as Lactobacillus. There are other microbe shapes, but these were the two that I had access to instead of shapes such as filamental or spirella, so those were the ones that were utilized. The second feature was size. Microbes vary greatly in size even if they have the same shape. For example, Streptococcus thermophilus is a very small microbe at about 0.5 to 2 micrometers, whereas Saccharomyces cerevisiae is much larger at 5 to 10 micrometers. Thus, they would be able to identify the difference between these two microbes depending on their size. I then moved on to the creation of my actual neural network. In this neural network, I utilized 11 layers with 6 different types of layers, including convolution, which is where features are extracted, and max pooling, which is where downsampling occurs. I then had to pick an algorithm for my neural network. The algorithm would determine how my neural network processed, and I wanted to ensure that it was able to support such a complex issue. I immediately eliminated sums such as polynomial or support vector because they would not be able to identify the small differences in these microscopic images. In the end, the decision came down to gradient descent or stochastic gradient descent. I chose stochastic gradient descent because of 2 main reasons. Firstly, it is able to account for the ebbs and flows of a neural network because it only utilized one training example in every iteration. Gradient descent, on the other hand, uses all the samples, which makes it so that it has only one local minima and only one local maxima, whereas stochastic gradient descent aims to find the absolute maxima and the absolute minima. The second reason was that it was able to have a much higher processing rate than gradient descent because of the reason that it only used the one singular training example throughout all of its processing. I then had to pick a learning rate. The learning rate would determine the size of the steps my program took from one point to another on the gradient descent. Too small would mean that the program would get stuck in a valley, and too large would mean that the optimum point is missed. In the end, I chose a learning rate of 0.01 because it had a medium processing time but a very high accuracy. I then combined all of these parts together for the training of my neural network. And here you can see that the training and validation both continually increased. Training was where my neural network learned for the first time, and validation was where I was able to fine-tune some of the parameters. In the end, the average training accuracy was 94.3, and the average loss was about 0.1. I then moved on to the prediction stage of my neural network. In this stage, my neural network would be given images it had not previously seen before and asked to identify them. In this, it had an average accuracy of 98.13 and an average F-score or recall rate of 94.25. As seen in this confusion matrix, it was also able to identify the various types and combinations of microbes correctly, thus proving it a success. I then moved on to the final stage of my design success criteria and of my research, the creation of my cohesive all-in-one device. This device had 3 main systems: the imaging system, which is where the microscopic images would be taken, the neural network or AI processing, and the transmission system, which would allow it to communicate between the water pipes and the water plant. For the imaging system, I created my own microscopic camera using a Raspberry Pi camera, an optical tube, a 10 magnification optical lens, and a 40 magnification objective lens, thus making the final magnification 400. This would be able to create a cost-effective microscope that's able to analyze these images and send them to the neural network as needed. Then for the transmission system, I used LoRa, or long-range radio technologies. These are able to transfer small amounts of data over long distances, meaning it would be directly applicable to my device because sometimes the site of contamination and the water plant are very far away. Now here's the end-to-end overview of my solution. Firstly, the neural network is loaded onto the Raspberry Pi. This is to ensure a portable and modular version of the neural network that can directly be implemented into the water pipes. Then, a cron job is scheduled to take images of the microscopic water samples at certain times. This image is then sent to the neural network for processing. The neural network then provides us with an output, and the output is converted into a contamination code. This code was created to reduce the amount of data that would need to be transferred in the transmission system. Because like I said, LoRa can transmit over long distances, but it can only do so in small amounts of data. So if I said the number 2, for example, that would indicate that there was lactobacillus contamination present, and that code being transmitted would be all that was necessary to identify the contamination and to tell the water plant and local authorities what next steps need to be taken. From here, I had a transmitting LoRa in the actual water pipe, which would send the contamination code and that classification to the receiving LoRa, which is in the water plant, thus facilitating communication between the 2 locations. Now, here's a quick video of my entire device working. First is the microscopic system. The microscopic system is utilizing the Raspberry Pi camera, the 10 magnification optical lens and optical tube, and the 40 magnification objective lens. Next is the 11-layer neural network with the AI processing, a stochastic gradient descent algorithm, and a 0.01 learning rate. This then provides us with the classification, and that takes us to the transmission system of the LoRa. This right here is the transmitting LoRa, which is converting that classification that the neural network gives us into the contamination code, and is then transmitting that contamination code to the receiving LoRa, which would be located in the water plant. Here is that LoRa, and that transmitting LoRa is then able to alert local authorities as needed and be able to consistently identify any contamination that may be present so that people are always kept safe and aware of what may be present in their water systems. Now, this is a great innovation that I'm so proud to have been able to work on. But like any good innovation, it is always in the process of being fine-tuned. So for my next steps, I want to continue to add new data and new amounts of bacteria and other microbes that could be utilized in water contamination by working with local universities. I want to use Google Maps API to create a neural network program that's also integrated with a mobile app so that we can be able to create a mobile application that people are always able to be aware of the contamination in their area. I also want to continue to improve my microscopic system by adding features such as a condenser, which will help to increase the quality and thus make my accuracies of identification much higher. In the end, I truly believe that with Nereid, we can change the world, simply one water droplet at a time. Thank you.